So thanks for the introduction. I'm Forrest Iandola. I'm with DeepScale. Previous to this, I did a PhD in the EECS department at Berkeley. And before I get started, I'd like to thank many of my collaborators, some of whom I'm sure I have forgotten to include in this list, primarily from UC Berkeley and DeepScale. This slide is going to, or this presentation is going to be about tips and tricks for developing smaller neural networks. And just to level set what it is that I mean by that, let me kind of go through some of the key techniques that are used to make neural nets faster and more energy efficient, and then point out the thing that we're going to be focusing on for the next little bit here. So we've got model compression. That includes a broad array of things, most popularly things like quantizing the network to fewer bits, pruning it, and things like that. Developing new layer types. I'm a big fan of the graphic used in the ShiftNet paper for the shift layer. This is just a representative example of the kind of thing you can do. Basically, I would say that almost any differentiable math, anything from your 3 semesters and probably over 1,000 pages worth of calculus textbooks, can go into new layer types. Original net design. This is basically, well, you look around CVPR, lots of people are using ResNet for this, and GoogleNet for that, and MobileNet for the other, and SqueezeNet. Those are all nets that somebody originally came up with, and there's no reason we can't develop more of those from scratch. Original net designs also tend to feed into model compression techniques, which may be automated or manual in the approach of how the compression parameters are chosen. Distillation, this is basically, at least a common embodiment of this is, the goal is to train a very small network, which we call the student. We've got a teacher network that's probably larger and a bit more sophisticated that's already been trained. And the goal is, instead of training to replicate the labels in the training set, we train to replicate the labels generated by the teacher network. And this tends to add some value to accuracy in certain problems where the goal is to make a small model. There's efficient implementations. This is, these can be co-designed with your neural net or just designed independently of that. I've found it can be quite valuable to kind of go beyond what the popular hardware vendors like NVIDIA with cuDNN or Intel with MKL-DNN currently offer. Naturally, those libraries are growing, but you can implement particular computations more efficiently for your hardware. And then finally, on the bottom right, design space exploration is both within each of the other 5 boxes as well as across them. How do we orchestrate this to find sort of the Pareto optimal frontier of best models given the constraints of your problem? So these are all very important areas. I've been fortunate in my career to have spent some time on most of them. But in this talk, my focus is going to be primarily on designing brand new neural net architectures that can be fed into most of the other aspects of this. So for the rest of the talk, I'm going to talk about these main things. So why develop small neural nets? I'll give some tips and tricks of the trade for designing small neural nets. I'll go over some proof points and interesting results with small neural networks. And then I'll conclude with an argument of why small neural nets are only becoming more important. So first, why develop small neural networks? So let me kind of just spend a minute to rehash the energy argument. So the black part of this diagram is the actual chip, and everything else is not. So based on some of the numbers from Mark Horowitz's Computer Architecture Research Lab at Stanford, you can see that if an addition costs 0.18 picojoules, this is all in a fairly vanilla computer architecture setup. Multiplication costs about 3.4 times that. Accessing an on-chip cache, an on-chip SRAM, which could be user-managed or automatically managed through cache eviction policies, costs 44 times more than an addition. But the big kind of blowout number is, as soon as you have to go off-chip for memory access, your energy requirements blow up by a couple of more orders of magnitude. And what's interesting about this is if you look inside anything ranging from a very small device to a cell phone to a GPU, you have this dichotomy of on-chip and off-chip. So with GPUs, I'm not even talking about CPU to GPU bandwidth or anything like that. I'm just talking about the memory that's contained still within the GPU card, but off the chip. So a lot of neural nets have parameters that don't fit in the on-chip caches, and they have activations that spill outside the on-chip caches, requiring lots of very costly memory accesses. And what this kind of illuminates is if you can develop a small neural net where all of the parameters and all the temporary variables fit within the confines of the chip, you will save a ton of energy. So let me go through one more aspect of why small neural nets have become so important. So I've been coming to CVPR for quite a few years now. And when I was a graduate student, one of the state-of-the-art GPUs to work on for some time was the NVIDIA K20. Trained lots of neural nets on these. And basically, the thing I want to highlight is, for every flop you do, in the time that takes, assuming everything's well batched and well orchestrated, you can do 17 of those calculations for every byte that you load, is what I'm saying. This is sort of a poor man's version of arithmetic intensity that I'm showing here because it's simple and easier to reason about. So basically, 3.5 teraflops per second is the vendor claimed peak. Around 200 gigabytes per second is the best case you can achieve in terms of transferring memory from the GPU's off-chip memory to on-chip. So I don't know about you, but it seems like at least once a month I hear about, whether it's in research or in industry, somebody working on another sort of tensor processing unit, which is promised to be ready quite soon. We've been hearing AI hardware is coming for a long time, and I think 2018 is the year a lot of it has actually shown up. So this is where NVIDIA claims they are with the NVIDIA V100. So going to 16-bit floating point operations, and when you're doing the sort of 4x4 matrix multiply operation that the NVIDIA hardware, NVIDIA tensor cores on the V100 are optimized for, you can actually get, according to NVIDIA, 112 teraflops per second, which is a lot. But what's really interesting here is, doing these tensor processing devices really optimized for matrix multiplication and neural nets has been a very sort of high yield thing to do, but I haven't seen any particular ace in the hole as far as making memory faster. So memory is sort of chugging along at a more predictable rate of improvement. So the memory bandwidth in terms of gigabytes per second you can load, NVIDIA claims on the V100 is 900. So we've actually increased by about an order of magnitude how many operations we have to do to keep the GPU busy for every byte we can load. Or basically, we have to be about 10 times more efficient or conservative with using memory bandwidth if we want to get anywhere near that 112 teraflops per second that NVIDIA claims. So basically, processors are improving much faster than memory. Given that this is a session on efficient deep learning, I should probably talk about mobile as well. So similarly, look back just a few years. One of the most efficient devices for doing deep learning or deep neural net inference on mobile devices just 5 years ago was the ARM Mali GPU. This is kind of the class below the smallest thing that NVIDIA sells. And they claimed, or I guess if you do the multiplication of how many vector lanes times how many megahertz, you get about 120 gigaflops per second. In terms of memory bandwidth, it's basic, just sort of single LPDDR3 memory, which does a little over 10 gigabytes per second, and the operations write ratio is about 10. This, for the time, compared to CPUs with operations write ratio is more like 3, seemed like, wow, we're sucking through a very thin straw to get all that memory in for our applications, but that's totally blown up here as well. So, Huawei has emerged with a tensor processing unit just over the last few months. They call it a neural processing unit, actually. It's available in phones that you can buy today, like the Huawei P20. And they claim around 2 teraflops per second using 16-bit. And it's just vanilla cell phone memory, though. So basically, again, we're drinking through this tiny little straw of memory bandwidth in order to get things in and out of that device. And I don't know as much about the NVIDIA Xavier yet, but Brian Catanzaro, our friend at NVIDIA, strongly encouraged me to include this here as well and check these numbers. And so basically, between what Brian said and these references, I was able to confirm, NVIDIA claims 30 teraflops per second or 30,000 gigaflops per second. I don't know exactly the memory structure, DDR what exactly, but 137 gigabytes per second. And this is the most extreme case I've seen to date of the tensor processing hardware just vastly outstripping what its memory hierarchy can do. So if not obvious, let me make this painfully obvious. So if you don't want to spend the rest of your deep learning life waiting for memory to load, we need to bring small neural nets to the rescue. So in this section of the talk, I'm going to go into some tips and tricks for developing small deep neural networks inspired by the design choices of SqueezeNet, MobileNet, SqueezeNext, and others. This, again, is sort of original net design. So if you're doing automated design space exploration, you still need to seed that with some initial neural network architecture. Somebody's got to be working on those. That often tends to be people like us. So I'm going to go over some things here that if you've personally hands-on been doing deep neural net architecture for a long time, will be fairly obvious to you. But these are things that you can go through an entire CVPR and have nobody ever sit you down and explain it. So I'm just going to go ahead and do that. So one of the observations that we had when doing SqueezeNet and the networks that we developed since then is that if you get rid of your fully connected layers as a general heuristic, you can save a lot of parameters. Now, why is that? So in AlexNet and BGG, the majority of the parameters are in fully connected layers, and in fact, just the FC7 layer in AlexNet has 4,096 input channels, 4,096 filters. You multiply those two numbers by 4 because it's floating point, and it's actually 67 megabytes of parameters, which is a lot. It's more than 10 SqueezeNets total. But I want to be clear, one nuance is it's not like fully connected layers are the culprit for high model size. Rather, the problem is that some neural net architects, like the ones who developed AlexNet and BGG and a broad variety of other nets, just decided to have lots of filters and channels in their fully connected layers, which leads to a ton of model parameters. Personally, I tend to make very minimal use of fully connected layers, maybe just at the very end of a classification network or as part of my sort of region classification in a detection network or something like that. But I found that keeping the same compute footprint, but moving it over to convolutions where you have some more activations and fewer parameters tends to lead to similar or better accuracy than this approach. Kernel reduction. So again, this is one that if you've been doing it for a while, you'll understand, but if you haven't, somebody's got to teach you. So basically, a lot of neural nets, convolutional neural nets use 3x3 filters kind of throughout. People talk about 1x1 filters. What does that really mean? Well, these filters are typically actually height times width times channels. There's that other dimension. So 1x1 filters turn out to be exactly, general matrix multiplication, where the channel dimension can be easily vectorized in your computations. So just some proof points on this. When developing SqueezeNet, we started with an initial neural net architecture of our own design and did a broad variety of sort of explorations on trade-offs between where to put the parameters and how the accuracies turn out. And compared to an initial model that we started with, that we described in the SqueezeNet paper, we were able to replace half the 3x3s with 1x1s and still retain the same accuracy. Beyond that point, accuracy started to degrade in a gradual manner. But basically, I think there are a lot of nets out there that still use 3x3 filters way too liberally. In SqueezeNext, 3x3 filters are mostly eliminated. So it actually has a mix of 1x1s, which are by far the most frequently occurring filter dimension in SqueezeNext, and also some 3x1s and 1x3s to help get that spatial resolution in there, or receptive field, rather. It's also important to pay attention to your number of channels. So, typically in convolutional neural nets, the default thing to do is for every filter to span all the channels that it's provided as input. And you get to choose how many filters you have, which determines how many channels are in the next layer. And if you cut down, from 256 filters, for example, to 128, and have that be the consistent setting, the one thing that's easy to overlook is that actually quadratically reduces your parameter count and not just linearly. So you actually go to a 4x reduction in parameters if you do that. So a little bit of change to these settings goes a long way. And last one of these I want to go through before moving on is Depthwise separable convolutions. This idea has been sort of implemented in deep neural net frameworks for several years now, but has only started to be really used actively over the last couple of years. Some people call this Depthwise separable convolutions, some people call it group convolutions, some call it fully grouped convolutions, and some call it cardinality. Each of those terms means something slightly different, but the basic idea is why bother having every filter span all the channels when you could have each filter span fewer channels and save parameters? And the extreme case of this is having a unique filter for each channel and each channel just spans one filter, which is the way that MobileNet does its 3x3 convolutions. This can really help with model size a lot, but beyond a certain point, you get diminishing returns and speedups for reasons that were mentioned in some of the earlier talks. In particular, that you don't get very high arithmetic intensity, and so fully grouped convolutions, especially on modern TPUs, you spend a lot of time waiting for memory to load. So let me go into some fun results of what people have been able to achieve with small neural nets, starting with some of our own work and then moving on from there. So, it's still interesting to kind of benchmark at a variety of different accuracy levels and sweep that kind of Pareto optimal trade-off curve of accuracy along with a variety of system-level metrics like model size and energy. So these kind of profiling results and energy savings come from Ki-Sok Kwan, who spent some time at Berkeley over the last year and is with Samsung. These are on some tensor processing hardware in a simulator that he's in the process of developing. I mean, the simulator exists, he's in the process of developing the tensor processing hardware, and this is on one of his sort of TPU prototypes. And so what's interesting here is the number of Macs from AlexNet on down decreases somewhat, but the energy savings actually decreases more quickly than the number of Macs. The reason, so far as we can deduce, is that the savings in model size and activation footprint tends to be at least as important, often more important, in terms of energy consumption. And as a result, SqueezeNext-small is a highly efficient deep neural net architecture. Other neural nets, like DarkNet, for example, were profiled in these papers as well. And then more at the kind of roughly 70% top one image and accuracy level. The interesting thing I want to show here about the kind of medium-sized version of SqueezeNext that's in the same ballpark as MobileNet's accuracy is that it has 25% more multiply accumulate instructions, but actually uses a little bit less energy. And again, that appears to be coming from two things. One is that SqueezeNext has fewer parameters than MobileNet, so that saves on memory access. And then unlike MobileNet, SqueezeNext, at least in this version, doesn't do anything with fully grouped convolutions at all. So SqueezeNext is more efficient with data reuse. So these are kind of featureizers or backbones that often underpin a broad variety of neural network activities, ranging from being initialization points for design space exploration, or being kind of the featureizer or input to other activities like object detection. So how does this all fit together? Well, so this paper literally came out this week from a group at Intel. And what's most interesting about this is in the Pascal VOC object detection data set. And what's really interesting here is there's a variety of different featureizers used, ranging from DarkNet to MobileNet to SqueezeNet to Fire, which is based on Fire layers that are from the Squeeze network. And I guess given this paper was brand new, I didn't have time to put this in, but what's interesting is each of these different featureizers actually has a significantly different accuracy on ImageNet, and those accuracies are a lot less correlated than would have expected with how well the models do on Pascal object detection. So I think going forward, what we're seeing is, how well you do on your pre-training or whatever warm-up exercise you do for your neural net before going to your real application is less impactful than we thought on the end accuracy on your final application. Perhaps one of the most entertaining applications of small neural networks is for those who watch the Silicon Valley TV show. The Not Hot Dog app in the TV show. You take a picture of something, ideally a food item, and it tells you whether it's a hot dog or not using a smartphone. HBO actually hired a small engineering team to build a real-world version of this app. They documented how they did that, and one version of it used SqueezeNet. The latest one uses MobileNet. Small neural nets can be used for a variety of things, including art. So in style transfer, the top result is from kind of this initial paper on style transfer by Justin Johnson and co. at Stanford. But by injecting the shift operator into the original VGG net that was trained for style transfer and building a net with shift, Bi-Chen Wu and co. were able to save a factor of 6 in parameters and still produce similarly pretty neural art. So I mentioned I work at DeepScale. You probably wonder what it is that we do all day. So let me just show you one example of the type of thing that we're working on. We've been a little bit conservative on publishing, but rest assured we will have another wave of papers coming out on these things shortly. So this is the type of stuff that we're developing for use in automobiles on the road. And on the left, we have object detection using monocular camera. And on the right, we have something that takes me a little longer to explain, which is basically we're doing 3D reconstruction. We're making something that looks and acts a lot like the kind of point cloud you get from a 64 beam Velodyne LiDAR, which costs $80,000. And we're doing that with around $1,000 worth of cameras and a very small LiDAR that's 16 times lower resolution than the Velodyne. So this is sort of a proof point on what you can do with early sensor fusion, taking a kind of a ragtag band of low-cost sensors, feeding them into a neural net that's been trained to replicate a much more expensive sensor. I don't by any means think it's time to move away from LiDAR. I think LiDAR adds a lot of value. It gives somewhat more detailed results around each object, for example, than this does. But, you know, LiDAR reliability is not where we would like it to be. These aren't designed for driving 200,000 or 300,000 miles in the lifetime of the vehicle. So as a fallback, this has turned out to be quite helpful. And also, we do a lot of work in driver assistance and collision avoidance software for lower cost vehicles that definitely can't afford a $10,000 to $100,000 LiDAR, and this has come in handy there as well. So my team has sworn me to secrecy on exactly how many model parameters are in these networks, but we will be publishing more soon. But we're from DeepScale, so you can imagine just how few it might be. Getting towards the end here, this is one last slide before I wrap up. And I didn't quite find a good place to plot this into the talk, so I just kind of wanted to go over it at the end here. So one observation is that the sort of quote-unquote right deep neural net is now increasingly more platform dependent. So what do I mean to that? Well, each of these different sort of tensor processing platforms is optimized for a different problem dimension and to somewhat a different use case. So the Huawei NPU is optimized for 3x3 matrix multiply. The V100, as well as a broad variety of NVIDIA hardware that has tensor cores, is optimized for 4x4 matrix multiply. The TPU, somewhat famously, does 128 by 128 matrix multiplies. And so if your problems don't fit neatly into these dimensions, it can be very challenging to get that huge speed up that's been promised. Off the record or under NDA, I've been told about even more exotic things like very specialized mass-produced hardware that does sliding window convolutions in hardware or sliding window operations more generally, very specific sizes. So my sense is that if we look at where efficient neural net design is in 5 years, the neural net that you're using actually has been designed for the particular platform that you're running on. You'll buy a device, there will be a variety of featureizers and other kind of base neural nets that come with it that either the research community or the hardware company have designed, and you use that as the initialization point for your design space exploration to develop the perfect neural net for your application. So this is my last slide, and if you take nothing else away from this talk, I think for the last 2 to 3 years at least, in the efficient neural net community, the old conventional wisdom has been that if you reduce flops, speedups will just follow directly from that. I think the new conventional wisdom is that flops are becoming a lot cheaper than they were before, and memory accesses are relatively more expensive, both for time and energy. And I think the conventional wisdom that we'll be staring at in a couple of years will be, given this kind of Cambrian explosion of different approaches to tensor processing hardware, some types of flops will be extremely cheap, other flops will be pretty cheap, and memory accesses will be relatively even more expensive than they are today. Just one last bullet point here. So neural nets are an infinitely large design space. Whether you choose to explore them manually, automatically, or somewhere in between, I encourage you to never stop exploring. Thanks a lot. Take questions now.
We have time for one fast question.
Hi, great talk. I'm just wondering, when you replace a 3x3 convolution by a 1x1 convolution, one would expect that would lead in a dramatic drop in accuracy because the 1x1 filter has the receptive field of just 1 pixel. Do you have any intuition of why that does not happen?
Sure. So I think, at least my observation is that receptive fields in neural nets are important, but not every neuron needs to have access to defining a big receptive field. So mixing signals across channels actually turns out to be a pretty important cue as well in deep neural networks. And even if just a relatively small portion of the filters have a way to kind of have a receptive field that they manage themselves, you can still actually get a lot of signal overall from the data.
And then I noticed that people are using convolutional filters with dilation now a lot.
Convolutional filters with what?
With dilation parameters.
Dilation,
So
yeah.
like a regular kernel would be dilation 1, and people are using larger numbers for the dilations. So the same kernel with the same number of weights will have a larger receptive field. Have you tried experimenting with that?
Yeah, dilations are great, especially for very high resolution images where you want more receptive field, but you want a parameter budget or a compute budget as well to be limited. Absolutely. Great. So one last thing before I hand the microphone back. On your way to lunch, we have some T-shirts and things you can grab on your way out with other DeepScale souvenirs. So feel free to do that as well.
This thing, the speaker again.